Thank you very much for attending this session. Today I'll go through a couple of exponential smoothing problems. This is the general form of exponential smoothing. Forecast for next period is equal to forecast for this period plus the gap between actual and forecast of this period multiplied by a constant which is between 0 and 1. We can a little bit manipulate this formula and come out with another version of it, which states forecast for next period is the weighted average of forecast for this period and actual for this period. Forecast is multiplied by 1 minus alpha and actual is multiplied by alpha. These two formulas are exactly the same as we saw. One is extracted from the other. In this problem, we have actual demand and forecast for the current period, and we want to forecast for the next period using alpha equal to 0.3. Forecast for t plus 1 is equal to forecast for t times 1 minus alpha plus actual for t times alpha. Ft is 70, alpha is 0.3, 1 minus 0.3 is equal to 0.7. That is multiplied by forecast times 70 plus alpha, which is 0.3 multiplied by actual, which is 60. Here we are in 2019. We have the actual, which is 850, and we have forecast, which is 910, and our alpha is still 0.3, and we want to forecast for 2020. Given the following data, demand in period 1 is 300, period 2 500, and period 3 600. What is your forecast for the next period using smoothing constant of alpha equal to 0.5? We know that the formula is forecast for next period is equal to 1 minus alpha times forecast for this period plus alpha times actual for this period. Alpha is equal to 0.5, we place it over there. 1 minus 0.5 is 0.5, and 0.5 itself is 0.5, so that is 0.5 times forecast plus 0.5 times actual, and that one is 1 divided by 2 forecast plus 1 divided by 2 actual. Therefore, we can simply write it as forecast plus actual divided by 2 as our forecast for the next period. For period 2, forecast is equal to 300 because we just take the actual of period 1 and assume it as forecast for period 2. And therefore, in period 2, I have forecast of 300 and actual of 500. Add them divided by 2, it is 400. That would be my forecast for period 3. In period 3, my actual is 600. 400 plus 600 divided by 2 is 500, and 500 is my forecast for period 4. Which one is better, a larger alpha or a smaller alpha? A larger alpha means we give more weight to the recent observation. A smaller alpha means we give less weight to most recent observations and more weight to previous observations. In one of my lectures, I will show it to you, I will mathematically prove it, that exponential smoothing is a weighted moving average. But all past data present in this weighted moving average. However, older data have smaller weights and more recent data have larger weights. When alpha goes up, it gives more weight to the most recent piece of data. So it will show fluctuations. Which alpha becomes small, any recent changes cannot have that much impact. Here I have asked you to forecast using exponential smoothing and alpha equal to 0.1, 0.2, and 0.4. Always we assume that forecast for the first period is equal to actual for the first period. And then here I have shown the formula. This one is multiplied by alpha, this one by 1 minus alpha, and then it will go there. And that would be 200. Again, this one is multiplied by alpha, this one by 1 minus alpha, and it will go there, and so on and so forth, using these formulas. You need to lock alpha, which is here in this case, because you copy it down, and therefore in all equations it should refer to that specific sum. Now if you use alpha equal to 0.2, these are your numbers, and alpha equal to 0.4, these are the numbers. In general, large alpha, more fluctuations, small alpha, more smooth. Our decision is based on MAD, MSE, or MARD, depending on which one do we want to use. Here I would like to explain this once again, that why we use MAD. Is MAD better or MSE is better? To my opinion, MSE is better, but why we still use MAD? It is because when they designed MAD, our computation capabilities was not as strong as today. Computing a large number of squares was not as easy as it is today. But absolute value is very simple. We just ignore the sign and we add them and we average them compared to square them and then average them. But dealing with absolute values in mathematical equations is not easy. Dealing with squares are much easier. Therefore, while mean square error is a better measure, and also in all mathematical manipulations, we are more comfortable with MSE these days, but we have still kept MAD because these concepts of accuracy measures initiate from those days when computing absolute value was easier. Here again we have another problem. We have actuals here. We assume the actual of the first period as our forecast for the first period, and the rest is just to put these numbers into the full. If this is column C and row 1, and if this is C1, then we should lock it. This is 1 minus alpha, and here is alpha, and we have multiplied them by forecast. So if this is forecast, and if this is actual multiplied by alpha, forecast multiplied by 1 minus alpha, actual, which is here, multiply by alpha, and forecast, which is here, multiplied by 1 minus alpha. Then we find A minus F, and then we compute the absolute value and put them here. And then this one is average of all these numbers. And if we multiply this one by 1.25, that will become this one, which is the standard deviation of our forecast. If you double click here, you can also see the Excel file. So it's better if you put these slides in slideshow mode and go through them, and as soon as you have a difficulty, then you can refer to my solutions. A forecast based on the previous forecast plus a percentage of forecast error is this, and that is what is the result of large alphas. Obviously, alpha cannot go more than 1. It makes our forecast more accurate, more responsive, random, stable, level, more responsive. By responsive, I mean as soon as we see a change in real life, it will be reflected in our forecast. For what value of alpha, exponential smoothing performs like 1 period moving average. Whatever we observe, we assume it as our forecast for the next period. Under what alpha? This is our exponential smoothing formula for forecast for the next period to be equal to the actual of this period. That means ft plus 1 should be equal to at. And this one should be 0. That is only possible if alpha is equal to 1. Therefore, if alpha is equal to 1, that is 1 times 80. And this is 1 minus 1 times ft. This will become 0. This is 80. 80 is equal to ft plus 1. For forecasting technique to become a straight line, forecast for period t plus 1 should be equal to forecast for period t. That is the meaning of a straight line. Therefore, if this is our formula, then ft plus 1 should be equal to ft. Therefore, 1 minus alpha should be equal to 1. For 1 minus alpha to be equal to 1, alpha itself is equal to 0. That means whatever I have observed in reality, I will assign a weight of 0 to it. Let me show you the impact of alpha. I right click on it, open Excel sheet, open. Look at here. I consecutively change alpha from 1 to 0. I make it 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, 0.05, and then 0. The orange line is my forecast. The blue line is my actual. See what will happen to the orange line when I change alpha from 1 to 0. Now it is 1, and therefore it is 1 period moving average. Actual of this period is considered as forecast for the next period. I make it 0.9, a little bit different because now I give a little bit weight to the previous data, but still 0.9 to the most recent piece of data. 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2. So you see, as I decrease alpha, the curve becomes more smooth. It distances itself from one period moving average. It will not just immediately reflect the changes in the actual data in the most recent period. Now it is alpha equal 0.2. If I make it 0.1, it is like this. If I make it 0.05, it is like this. And if I make it 0.03, for example, it is like this. And if I make it 0, 0.03, 0.05, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. We have used exponential smoothing. Our current forecast, 66, was 5 units larger than actual demand. So we have overestimated. Forecast for next period is 65. Previous period 66 was more than actual demand. We have brought it a little bit down. Now it is 65. What alpha value have we used? FT 66. It was 5 units more than actual. 5 units more than actual. But this is actual minus forecast, so I should put negative sign over there. And forecast for next period is 65. 65 is equal to 66 plus alpha multiplied by minus 5. One equation, one unknown, and alpha is equal to 0.2. We know that in moving average, if n goes up smooth, that means it becomes smooth. The curve becomes smooth. And we also showed that in exponential smoothing, when alpha goes down, the curve becomes smooth. So if alpha goes up, the number of periods should go down, because if alpha goes up, it will be more responsive. And in moving average, which one is more responsive? Larger number of periods or smaller number of periods? Smaller number of periods. Therefore, the answer to this question, the larger the alpha, the larger periods in moving average, is false. The larger alpha, curve is more responsive. That means the smaller the number of periods in moving average if they want to be of the same age. Age of data in exponential smoothing is 1 over alpha. And therefore, if alpha is equal to 0.5, 1 over 0.5 is equal to 2. So if alpha equal to 0.5, age of data is 2 periods. If alpha is equal to 0.2, that is equal to 5. Here, age of data is 5 periods, average age of data. Age of data in moving average is equal to n plus 1 divided by 2. And that is 2 equal to n plus 1 divided by 2. That is n plus 1 equal to 4, and that is n is equal to 3. Therefore, if alpha is equal to 0.5, age of data is equal to 2, and it is equivalent to a moving average with 3 periods. If age of data is equal to 5, that is equal to n plus 1 divided by 2, that is 10 equal to n plus 1, and that is n equal to 9. If alpha is equal to 0.2, the age of data, the average age of data is 5, and that is equivalent to the 9-period moving average. So when alpha goes down, number of periods in moving average goes up, as long as it goes to the age of data and as long as it goes to creating a more smooth curve. And it is for alpha equal to 0.1 when age of data is 10 periods. And that is equivalent to 19-period moving average. Given 6-period moving average, what is average of data? 6 period. The 6 period, the newest piece of data is 1 period old. The oldest 6. On average, 6 plus 1 divided by 2, that is 3.5. Exponential smoothing with what alpha is equivalent to 6-period moving average. 6 plus 1 divided by 2 equal to 3.5 equal to 1 over alpha. That means 3.5 alpha is equal to 1, and alpha is equal to 1 divided by 3.5. I think that is something around 0.29. I remember that because this is some computations I did for moving average of graduates at CSUN over 6 years period. Thank you very much for your attention. I will go through some mathematical proofs. That is just I wanted. Frankly, you don't need to be worried about it. Thank you. As I said, I will prove that exponential smoothing is weighted moving average. I proved that sum of the weights is equal to 1, and I also proved that the average age of data is 1 over alpha. But don't worry about it. Thanks.